Hello, I'm Kamaleshwaran, leading the redispatch team at iPLON. What is redispatch? So, redispatch is nothing but it's a modern way of dispatching the renewable energy resources from the generating station to the distribution and also to reach the end customer. So, the ultimate aim is to all the renewable energy capacities which we are building up in India should reach the end users and customers. So that's why we called ourselves as a redispatcher team, and we are working for effective management and modernizing the redispatch workflow. So how it can be done? So that is where the power plant controller come into picture. So the power plant controller segmented from small scale microgrid to like small PPC to the bigger utility plants, the larger PPC, and it goes to the master PPC as well as the hybrid PPC. And as part of the redispatch team, I'm going to talk about how we are managing the software. So the industries is needed or asking us to hold the responsibilities to maintain the software for longer period of time, 5 years, 10 years, 20 years. So someone should take the responsibility to maintain the softwares. It has to be keep updated and should be all the security patches and regulation patches need to be done on time to time, because the renewable energy is intermittent in nature. So depending upon how it's going to be progressive in our grid, the regulations and standards need to be continuously changed. Those things also need to be adapted as part of technology and modernizations for the product which we are supplying, and it should be used stably for a long time. And we are here to support. So how we are going to support? So that is where the modern technologies which the information technology and cloud world is equipped with. So those technologies we are using to update all the softwares which we are building and delivering to our customers. So in that way, hope you are aware of what are the tool chains which we are using. So how we are going to maintain these tool chains, and how we are going to be good support to our customers to handle these tool chains for a longer time with all the stable updates and security updates. So that's where the DevOps practice come into the picture. So you might heard about the DevOps. DevOps nothing but development and operation. So in the development and operations, it majorly comes from the cloud and IT world. And if you see the power plant environment, it's nothing but where the operation technologies like inverters and energy meters, turbines. So there are operation technologies which used to convert this renewable energy resources as electrical energy into the grid. So these operation technologies need to meet the information technologies, IT world. So to modernize the power plant as well as to modernize the grid. So in this aspect, if we are deploying the information technologies, tool chains and softwares into the power plant, then someone need to be there to maintain those things also. So if we are going to supply these tool chains and information technologies to your power plant or grid, then we are here to maintain those softwares and tool chains as up to date with the security patches for a longer time, or as long as we are going to use our product. So to do that, we have to equip with some other infrastructure to achieve those goals. So those infrastructure, iPLON is already using it. That's where we are using Google Cloud as a main platform to achieve those aims. So in Google Cloud, we have different tool chains for this infrastructure. Say example, in this DevOps, we have made all our softwares as a containers, as Docker. So in this Dockers, it will be like inventory. So all this hardware and everything need to be stored in the warehouse. So whenever needed, people take from the inventory the hardware and dispatches to the suppliers. That is where we have the software inventory and also delivery inventory. So software inventory, that is a separate tool which we are using, where we could able to understand and see all the tool chains and packages and its versions supplied as part of the power plant controller in cloud. So that is where we could able to monitor the tool chains, and if something's happened to like servers, it might happen, some hardware problem can happen, or because of the environment or natural disasters. There are a lot of things will happen during the operations time. So that time, how we can quickly respond. So we have the production inventory. Then in the DevOps world, it's called as Artifactory. So Artifactory management tool. So that is where we are using Harbor. This is a powerful tool which we have deployed in Google Cloud, where we are maintaining all our production grade Docker containers which is running in the power plant controller in Harbor. That is what you are seeing in the screen. So where we have the different kind of container and its related images stored onto it. So we no need to worry about something happen to the hardware or our panels or some accidents. We definitely able to quickly deploy all the softwares within a day. We could able to up the system. So how we can able to do that? So that is where we have another tool called the VPN. We are using the Open VPN. So through the Open VPN, our Google Cloud and the Edge, where the power plant controller is running, is connected. That is depending upon how this IT securities and workflows which the customers and power plant owners is following up. So it's not that the virtual private network, the VPN connected continuously. So whenever, because through the firewall we can enable and disable the connectivity. So during whenever the software patches and security patches need to be updated, like 1 day or 2 days, during that time only it can be enabled. So that time our power plant controller will connect to Google Cloud, to the VPN, to Harbor, and will get all the updates. How it can be done? That is where we are using Ansible configuration and package management. So Ansible, we have the playbook. It will take all the packages from Harbor and download it to the Edge devices which we have supplied as part of our plant controller, and execute those packages one by one. And also it will notify to us that whether all the packages installed successfully, error free. If something error is there, then our team will rectify those errors also. So that way we could able to effectively manage all these software changes and updates time to time, and give our good support for a longer time. And you also know that the technology is changing every second, every minute. There are new updates, new changes, new regulations, new advancement is happening. So our team is made in Mylapore. So the product is made in Mylapore. All the research and development is happening here, and we could able to understand what's going on in the Indian market, renewable energy sectors, what the government regulation is saying. So we could able to quickly make the changes, our upcoming releases for the new product segment as well as the existing product segment. So those updates also we could able to give to the customer by obeying their cybersecurity policies and compliances. So because our team also equipped and have good understanding of the customer cybersecurity workflow is nothing but CEA cybersecurity guidelines for the power plants. So because all the project developers and power plants following the CEA guidelines or has to follow the CEA guidelines not only for the electrical grid but also for cybersecurity. So our team also well aware of the guidelines, and we could also able to support and follow those guidelines to handle the power plant control system as well as those updates. So that's why you are in the safer hand with iPLON redispatch team for the power plant, and we will help you to make sure that the renewable energy generated at plant level to reach the end customer without loss. So thank you.
Hello, good afternoon to everyone. Very happy to be a part of this renewable energy community, and my name is Bharat, and I'm responsible for the product development of power plant controllers. Before we get into the details, just want to give you a little bit of background. Where is this application used and what is the need in the market? Yeah. So, I mean, everyone will agree with me when I say India is moving in the right direction. There's a lot of renewable energy addition to the electrical grid, and just to give you some numbers, now it's about 30% of the electrical demand is coming from the renewable energy mix, which is a very wonderful thing. But on the contrary, the so-called system operators, we call it as grid planners, they are facing a lot of challenges in to manage this addition of renewable energy into the grid. Yeah, I mean, we've been hearing a lot of these things, which is, I mean, just to give you an example, a few years back in Tamil Nadu, a lot of these wind plants were completely shut down due to some grid constraints. Yeah, so basically a very sad thing. As a solution to tackle this, there are a lot of measures which the government is taking now to make the grid more resilient and more digital to accommodate this addition of renewable energy. One such is smart grids technologies, where iPLON also fits in well into this domain. So we, in the last 2-3 years, we have spent a lot of time traveling to the sites, talking to the different stakeholders, like the system operators, been having a lot of discussion with the inverter OEMs, and we have a good experience now in this grid stability market. We call it as the product what we have developed for this market, we call it as the power plant controllers. So basically these are also called as grid congestion components. It's basically helping the system operators. It's acting as an interface between the plant and the system operators to efficiently manage the flow of renewable energy from the generation into the consumers. Yeah, so there have been a lot of white papers, discussions going at the background to make this whole grid into a digital era. And iPLON is also now feeling very comfortable. Like I said, we have been spending a lot of time and we have also good experience now in the Indian market installing these power plant controllers for utility scale plants, and we are also positively looking forward to take this to the next level. But probably in the next 2 years we will also be approaching a lot of these international customers, and one important competence what iPLON now has is also a support infrastructure. We call it IGOP, Global Operations Platform. So these are the engineers which are basically responsible for performing remote maintenance activities. Basically, for all the assets what iPLON has developed in the field, we have also have a good support infrastructure to maintain these for its life cycle operation. Yeah. So there is also a need for multi-domain skill set in developing these kind of grid stability solutions. Yeah. So we have people who are power system engineers who understand the energy flow from the generation, and then how is it transmitted to the high voltage network, and then how it is stepped down to the distribution until the time it reaches to the consumers. Yeah. So we have people who understand this energy flow, and they also have skills who can do the simulation program with the software tools like PSCAD and PSCC, because this is becoming very important in terms of grid planning and basically for the system operators to maintain or to have this kind of a predictive maintenance for this energy flow. Yeah. So that's one part. And the other part, which is also very close to iPLON, is the observability model what we have developed for these power plant controllers. Yeah, so that's from the technology front. So that means how do we collect the data from the field and the software stack, what we call as observability, and how we process it inside our engine, and finally how the operators visualize it to basically have the set points to control the output of the solar plants. Yeah, so that we will also be explaining in detail in a separate session. And around this system, cyber security is also very a critical factor, because we have also seen CEA laying guidelines for all the critical infrastructure like the telemetry data, the inverters, inverter-based resource plants, and also power plant controllers. There is a set of protocol that is laid to basically comply with those standards, so that the risk with this interoperability of data to different devices, they are minimized with this secured mechanisms. Yeah. So this multi-domain skill set is also one of the strength of iPLON. Like I said, we also have the R&D here, and there is also a separate operations team to look after the plants and also stay close to the customers to maintain the assets for its life cycle duration. Yeah. So we are very excited to be in this space. We are a very young team, very motivated engineers, and we are positively looking forward to grow together with the industry. Yeah. So we'll be very glad if you can also join us in this cooperation. Thank you.
Hi, I'm Satyanandan, working as cybersecurity engineer in power system at iPLON India. So today I'm going to cover about the cybersecurity topics that are mentioned by the CEA guidelines. So basically, as earlier mentioned, there is a high penetration of renewable energy market and renewable energy sources in the electrical grid. So this should be addressed as well, because it also consists of an OT and IT platform, operating temperature and operating technology, as well as an information technology. So we must ensure that these operating technologies, all these softwares, all these hardwares are ensured to be secured and also cyber secured, to ensure that they are reliable and they are operated by the person who they are to be operated by. This is also being stated in the CEA guidelines of cyber security, that is Central Electrical Authority cyber security amendment based on 2019 and 2021. So we are going to have a deep delve into the cyber security controls that are being provided by the iPLON Edge service and the PPC. So this is going to be a brief overview of the CEA guidelines and cyber security controls that are going to be present in this agenda. So the agenda is to CEA guidelines of the power sector, so how guidelines of cyber security are to be implemented in the power sector, and the security for cyber security, it includes the certification of 27001 certification, 62443 compliance, 60850 compliance, and 61850 compliance, along with a brief overview of all the cyber security controls that are being implemented by iPLON for the PPC systems, and also the policy policies of the IT and OT asset management, including the system. It starts from system configuration and security configurations. We also do vulnerability assessment and penetration testing of this system to ensure that they are up to date, to ensure there is no breach of cyber security and there is no breach of security controls in our PPC system, since they are a critical infrastructure equipments. So the CEA guidelines state these 14 articles as the framework for cyber security in India. So these 14 articles represent what are the controls that are to be established in the cyber security field for PPC, basically in IT and OT systems as classified. So the articles one speaks about the cyber security policy that needs to be implemented in place, and that brings the framework for the cyber security in the power system. Article 2 and Article 3. Article 3 describes about the appointment of CISO, Chief Information Security Officers, as well as a recognition of a critical infrastructure. And since our power plant control is a critical infrastructure, we have cyber security controls in place to ensure that it is cyber secure. And we also have electrical security perimeter in Article 4 and 5. And Article 6, 7, 8 and 9 describes about the workflow of cyber security framework, how cyber security framework should be established, and how the cyber security workflow should be implemented in the plant IT and OT. Article 10, 11, 12 and 14 describes about the incident reporting, sabotage reporting, and what are the steps that are to be taken after a breach of a cyber security incident if it occurs. Generally, coming into a part of cyber security, it is just referring to an organization's dedication towards having their hardwares and softwares to be in a secure state, just to ensure that there is no intruder that are being using the system, and there is a high availability of the system accordingly. And also the system is doing what it is intended to mean, like not running any other softwares other than it was intended to run as. So coming into ISO 27001, iPLON is ISO 27001 compliant company. So we take cyber security as a top priority to ensure that our system are very secure with enforcement of organization policy and encryption, hardening of our servers, patch management and application infrastructure, threat intelligence, network security, as well as overall system security to ensure that our system remains secure and stable even in the wake of an attack. The iPLON PPC is in compliance with the IEC 62443 protocol. So the IEC 62443 protocol defines the industrial automation control standard for the operating technology. So we are compliant with the IEC 62443, which includes security technology for ISES and how an operating technology and information technology should be segregated along the lines of network, and who should have access, including incident and access management, identification access management systems, as well as protected hardened systems. So these and all fall under the IEC 62443 protocol. So we are compliant with the IEC 644 protocol, and as well as the iPLON's PPC system are also in IEC 62443 compliant systems. Then coming into IEC 60870, so the IEC 60870 defines the standard for power system monitoring and control. So we also have this IEC 60870 protocol built into our system to ensure cyber security is at compliance with IEC 60870 standards, to ensure that the monitoring part and the power control part and network part is also included. And the 61850, we are also in compliance with the IEC 61850. So the 61850 describes about the use of intelligent electronic device, since our device is an IoT based intelligent electric device. So these standards are applicable to our systems also. Bitwarden. Coming into the part of cyber security, iPLON is committed towards providing cyber secure solutions to our customers. So all our applications and all our software are password managed to ensure that there is no intrusion into the environment without any undue permissions. So we deploy these kinds of software like Bitwarden software. So this Bitwarden software will enforce a password policy to ensure that there is no device there is no malicious intent to attack. Even if an intent to attack takes place, it will be stopped by the bit warden to ensure without no correct user credentials. And coming into a centralized IT asset management, we have in place the software called OCS inventory. So this software will have a list of entire edge devices, edge servers, including PPC that we have deployed in our fields. So this will monitor these OCS systems. This will monitor these edge servers time to time to ensure that there is no any breach of operations, or there is no any breach of cyber security violations. And also to ensure to our customers that our systems are safe and secure, and also we can remotely monitor these systems to ensure that there are no issues that are being there are no issues in the operating and IT systems. And server cyber security control, since at iPLON we use edge server cyber security control, we have classified our cyber security controls into different parts, including level 1, level 2 and level 3 sort of security controls. In our level, in these controls we have different types of methods, including hardening, encryption, and communication protocol itself will be a part of a cyber security protocol. So these and all will be explained to you in an overview state of the iPLON device. We also encrypt our edge servers to ensure that the physical data as well as the digital data should not be fall into the hands of any other person that does not require the information. So we are committed to, as earlier mentioned, iPLON is committed to provide cyber security and be cyber aware of all the threats, including our PPC systems. So to ensure this, we use encryption methodologies, that is AES-256 based encryption methodologies, and our servers are also hardened based on center of CIS compliant, that is Center for Internet Security based hardware hardening, software hardening. So our systems are hardened to ensure that the system image file is not raw, and the image is being hardened, and the access is being stopped to a certain extent to ensure that there is no availability of super user or privileged access to every user that is handling the edge servers. So this is basically like what is the difference between an unhardened and unhardened system. So an unhardened system will be a raw file image that is fresh from the internet. So this operating system will be open to interrogation, and it will have the least amount possible of cyber security controls. But a hardened system will have a higher standard of cyber security controls, which will also play a major role to prevent data leakage. So DLP, it is that. It also includes aid for Ubuntu, that is automatic intrusion detection environment. We have these controls in our system along with other controls. Coming into vulnerability assessment and penetration testing, VAPT is a very major part of iPLON cyber security standards and protocols. We ensure that all our edge devices that are leaving our premises is vulnerability assessment and penetration testing tested. So we also check these systems after installation of all the softwares that have been previously mentioned with their functionality ready. We also do vulnerability assessment to ensure that there is no vulnerability left behind, to ensure that no backdoors or no access to other systems are being given to iPLON system. Also, we do a penetration testing by ourselves to ensure that there is no sort of backdoors to be entering into our servers without our knowledge. And coming into the server and endpoint security architecture, so this is the basic overview of mostly all of the cyber security controls that are in place at iPLON systems. So at OS level security, we have control access to the BIOS system as well as encrypted with the full disk encryption. And basic level security, we have a user account control, identification and access management, along with the patch management and malware software inventories. Coming to network security, we also have web filtering present in the PPC system, along with open VPN architecture for remote monitoring and remote checking of the systems, along with system firewall that is included in the system. And access management once again plays a vital role in iPLON's security controls. It includes incident identification and access management, and to have a privileged user access pass and also segregate users based on the roles and responsibility of the user that are being provided with. And coming into log management, we also have certain controls that we also in the case of an event of a cybersecurity threat that is being ensured, we also use log trafficking and log analysis to ensure that what has went wrong, and also to enforce these policies. We also have a security controls team ready at our disposal. So yeah, thank you.
Hello, this is Vani. I'm working as embedded software developer in iPLON, and I'm happy to be the part of iPLON family. I'm going to explain about software stack, what we are using in iPLON for bigger utility plans. Because for bigger utility plans in India, people like to have different SCADA control solutions, where this OpenStack framework is useful for different control techniques and log customized algorithms, and giving the operator flexibility to control the plant and better handling of the devices. When it comes to the software stack, first layer will be the field devices. In the sense, the field devices is like inverters, weather stations, energy meters, and all. So once data is collected from the field devices, it is parked inside the hardware. From this hardware, we have to send this data to the databases. So here InfluxDB and Postgres are the databases what we are using. All the real-time data will be stored into the InfluxDB, and the alerts and alarms will be saved into that Postgres, and also the logging commands which was given by the operator also, those will be sent to the Postgres database. And next comes the iPLON middleware. So where we are having iPLON flow engine. So in this we are having the algorithms, iPLON algorithms, which will communicate with the databases for the data processing. So this part can be taken care by the iPLON flow engine. Basically it is like ETL pipeline, extraction, transformation and loading. And next comes to the PPC controller. So for communicating with the field devices or to control the field devices, PPC comes to the picture. So according to CEA guidelines, all the configurations have done for active power, reactive power, voltage and frequency controls. So in this algorithms are built like it has to control the field devices for better handling of the devices, and also to keep the grid parameters stable. And next comes to the visualization. Here we are using Grafana screens for visualization. This complete comes under plant level customization. And next comes to the we have to send this data to the headquarters, where there will be analytical team sitting. So they will analyze the data and they will give better instructions to the operator. So for that we are using OPC UA protocol. And to weather stations also we have to send the data. For that we are using FTP protocol. And for load dispatch centers also we will be sharing the data. For that we are using IEC 60870 protocol. And on top of that there will be the cybersecurity, VPN and firewall. VPN is like virtual private network to access the devices remotely. Whenever there is an issue or any support needed by the customer, then we can access our devices remotely and we can give support to them. So this is the IoT toolchain architecture. So here it will be the field devices where we are going to communicate, and after that there will be a server. Inside this server there will be Modbus protocol running, which will read the data from the field devices, and it will be sent to the database InfluxDB to MQTT. And from InfluxDB there will be a visualization tool called Grafana, and there we can visualize all the data, like all the real-time data and alerts and what and all will be sending to InfluxDB. We can visualize in Grafana. And there will be a Modbus virtual server running inside our server, where this acts as the bridge between the PPC controller and the field devices. So whatever the data reading from the field devices is sent to the PPC controller through Modbus virtual server, and the controlling also from the PPC controller is done by this virtual server, and this is complete flow running in Edge. So we'll be having this complete flow engine running in cloud also, where the data is sent from the field devices, real-time data, to InfluxDB through MQTT, which is running in the cloud. Here we are using like multiple IoT tool chains like MQTT, Modbus, InfluxDB, Grafana. For better communication between these tool chains, we will be making a containers and saving into the container registry called Harbor. So according to the project, our people will use these containers and build their Docker images. Thank you.
Hi, I am Faroz Khan, Power System Engineer, handling power plant controller projects and simulation. Nowadays, renewable energy penetration into the grid is high. So that so many renewable energies penetration into the grid, it causes the grid stability. So that a solution for the grid stability is to maintain the grid stable. That only solution is power plant controller. Basically, utility scale projects as per the Central Electrical Authority Guidelines Amendment Act of 2019. So if the power plant more than 10 megawatt at the range of 33 kV voltage level, they must have installed the power plant control in the site. And then they also have provided so total overall plant simulation also they have to provide to submit as part of the basically its simulation is for the preventive maintenance. It's able to how behave the sites, how it's if we integrated with the grid, how its grid behaves. So basically it's for the steady state analysis and dynamic state analysis. So for steady state analysis purpose, normally it's able to simulate. For dynamic state analysis, they have to PPC also play the roles in the dynamic analysis. So that if you install the PPC in the site, they have to submit that dynamic overall plant simulation report. So that they have the required the PPC model for simulation. So in iPLON, we have not only installed the hardware, the PPC, we also prepare that digital type of the PPC is in the PSCAD software. This is the PSCAD simulation for the PPC. Basically, this design is based on our hardware, how its hardware performs, same as it is that simulation perform. So it's actual. After that, after install the PPC, they can compare the simulation result and then the actual PPC result. They can compare and that both are same and submit the reports like that. So basically, we prepare the iPLON PPC as per the Central Electrical Authority guidelines. So what guidelines speaks? No, totally, we have that two modes of control. One is open loop control, another one is the closed loop control. So open loop control is nothing but what are the limit want to produce the inverter. Just click and write to the inverter. That's all. Nothing taken for reference from the grid meter, and so nothing like that. For closed loop control, it's take the reference. That means the closed loop. It's get the feedback from the PQ meter installed in that feeder level meter. So that we take reference from the feeder meter and now compare with the actual. That's the controls. The logic calculates the values to sending to the dynamic limit to the inverter. In closed loop control, so we provide that 8 different modes. One is the active power, reactive power control, voltage control, frequency control, power factor control, LVRT and HVRT control, and then ramp control, and then SVG mode control, night Q mode control. So different 8 modes are there in the closed loop control. So this all the modes are we build the logic as per the Central Electrical Authority CEA guidelines. So basically for active and reactive power control, what CEA says means if you the set point limit, what are the end of the day, end of the plant grid meter, what megawatt you want, that only if you give the set point as the set point to the PPC, it's up and down. It's basically it's do like that, track that set point only, achieve the result. So for voltage control, the CEA what speak now, so that we observe during the low voltage condition, generate the reactive power. During the high voltage condition, observe the reactive power. How much we observe, how much we generate. That's all the CEA guidelines speaks. For frequency control, so 2 type of group control is there. So if frequency range is 49.97 to 49.7 or 50.03 to 50.3. This kind of the range we follow the loop control. That we can curtail or increase the active power at the rate of the percentage 3 to 6%, not more than that. So if frequency range is 49.7 below or 50.3 above, that's the range 10 to 100% we can curtail and increase the active power. That's the frequency control. For the ramp control, we can slowly improve that active power. That means say as per the CEA, we can improve the active power 10% plus or minus 10% per minute. So these are the CEA. In iPLON, we build the logic as per actual what CEA speaks. That's only we implement the logics. This is the iPLON architecture diagram. So I previously explained that we get that closed loop control. We get that feedback from the PQ meter. So basically, in the site, inverters connected with the transformer connected to the grid. So depending upon the site's feeder number of feeder, which will vary. So we take as the example for the 2 feeder. So we take this is for the iPLON redundant architecture. So for the redundancy means if one server controller fails, secondary it's take the action. Again primary comes to the picture, secondary down, primary perform as it is. So if controller fails also, control didn't stop, so control takes place by the secondary, so that nothing will happen. So we maintain that site as the stable. This is for architecture for PPC. So I earlier explained the open loop control, so 3 different modes, and closed loop control, totally 8 modes are there. Also, if you want to values to the SLDC for telemetry purpose, also we can value to supply to the SLDC telemetry value also. So we have a standard process for the power plant control. That's what we contain that whole process. Basically, before if we first we carry the quotation, we send the person to the site. We test that site qualification test. So if site is capable for PPC, that inverter have the multi-client mode or not. So inverter is capable for control that active power and reactive power. This kind of the test that engineer test that all those things. So after that site qualification test, if the site is capable for the power plant control, so we after that PO we have the certain process. First process is the system under test. This is for our CDS system, nothing but Chennai development system. So as per first we collect the data from site team. So basically for SLD, single line diagram, and each inverter IP addresses, all those things we collected, and then we simulate in the CDS systems all the logics and all what are the requirements from the customers. So based on that, we well simulated. Once everything fine, then only we prepare the box and install those software in this box. So we conduct the factory acceptance test. So after the test, we ship that equipment. After that equipment, our engineer come to the site. We test all those 8 controls is working fine or not. We test as per the draft NLDC test procedures. So if as per the NLDC, in August, NLDC released the draft test procedure. As the test procedures, we have to conduct the test for active power, reactive power, all those controls. We have test and submit the results. These are the process. We have the implement in nearly 6 sites around 700 megawatt ranges. So it's well efficiently working and better. Thank you.
Hi, I am D. Ramani Chiara. I am working under the business development team. So we used to manage a project in the different stages. So once a sales team get an inquiry, we will make a AD and offer and assign to that particular project. So we will create the workflow for that particular project and assign to that particular project. And we will make a AD and architectural drawings and the engineering drawings. So the hardware assembly team will start their work, and we will also make a system description file and a plan description file, so that the development team start their software part. So business development team is like a bridge from the sales team and the development team. So we used to manage a project and follow the team members, and we will manage each stages of the projects. And I will be showing the workflow for the particular project. So once the projects come, these are the workflow we are following. So start from the project management to the handover. So first one is project management and the ETC pre-visit site and the system engineering and software and the hardware and that is factory acceptance test and ETC and then handover. And then coming to the project management. In the project management, we will start with the kickoff meeting. So in the kickoff meeting, it is an internal meeting with the BD team and the sales team and the project members. So in that, we will be start from the sales, start from the PO to handover. We will make a time tracker. So what are the actual time to complete that particular project? So this will helpful for the further projects also. And then the Bitrix Scrum. In the Bitrix, we will be creating the Scrum for the particular projects. In the Scrum, there are in every project we will create the 6 tasks for the particular project. So start from the kickoff meeting and the advanced drawing, hardware assembly and design engineering and system integration plus fact and delivery ETC and warranty AMC phase. So these are the 6 tasks we are following for the each project, and also we will create the drive. In drive also there are a 6 tasks. So what are the documents we are doing for that particular task, we will uploading here only. Like here you can see from project management to the handover, you can see like inquiry plus pre-sales and sales, PO, software integration and fact and delivery ETC handover. So what are the documents we are creating for the particular task, we will upload here only. So this is a drive for the particular projects. And then the project delivery and the commissioning. So the project delivery and commissioning is between the iPLON to the customers. So what are the main tasks which we are completing in the particular week? And then SDF is a system description file. So in the system description file, we will be mentioning the parameters like register, Modbus and data type for the individual devices like inverters, energy meter, etc. And then the PLDF. So PLDF is a plan description file. So in this, we will be mentioning what are the devices connected to the plant like the inverter, energy meter, annunciator, relay, etc. So in this we will be mentioning the make and model of each devices. So this will be mentioning in the plant description file. Thank you.
Hi, I am Rahul. I am working as a power system engineer at iPLON India Private Limited. I will give live demo for the 50 megawatt solar power plant at Andhra Pradesh region. This is the screen. This is the control architecture dashboard. This dashboard is designed as per the site structure. We have designed this dashboard. Here, these are the inverters for this 50 megawatt site. 20 inverters are there. 11 blocks are there. Each block has 2 inverters. These 11 blocks connected to the 4 incomers. 4 incomers connected to the 2 outgoing feeders. This is the size sector. This outgoing feeder level is 33 kV. Here, this is the inverter level is 0.66 kV to 33 kV. Is the outgoing feeder of the 2 energy meter. Here we can take reference from our PPC box, and the operator set the set point limit, and it will directly control to the inverter. As per the size structure, we have configured this dashboard, and this is the power control overview screen. This screen is designed as the site in charge operators and site managers to take decisions and optimize the plant performance. So we have configured this screen. This is the heart of the screen of our PPC. In one screen we can check all control data points and what are all the loop is on and off, which mode is on and off. So the operators we can check this one screen. We are providing solution of 2 modes of operation. One is open loop control mode and closed loop control mode. If which mode is on, it indicates it's green color. It's red color means it's off condition, and which feeder is on and off. So we can check here which mode is off. There are 2 modes of operation. In closed loop control mode, we have 5 control mode options: active power control, reactive power control, frequency control, power factor control. And the operator can also check which mode is on and off. So you can check this screen, and this is the actual data of the active power, reactive power, power factor, voltage is the feeder wise, and this is the operator set point limit. What are the set point set the operator? Here we can check what is the active power limit set point, reactive power set limit set point, voltage set point, power factor set point, frequency here also check. Similar to the feeder 2 also. Here this is the overall plants. Overall plant means overall plant active power, what is the reactive power, voltage, frequency, power factor, here we can check. And this is the inverter heat map. The inverter heat map shows the each and every individual inverter active power and their limits, reactive power and their limits. The inverter heat map, for example, the greater than 75% of inverter capacity, it shows green color. For example, 50 to 75% it's blue color. For 50 to 25% it's grey color. If 0 to 25% is yellow color. If not communicating, it shows red color. This is the power control overview screen, and this is the closed loop UA set point. The operator, here we can set the set point limit. In closed loop control, whatever the set point limit the operator set with the feedback from the energy meter. Feedback from the energy meter is controlled by our logic, will run through control set limits. Here the active power control set point, reactive power control set point, voltage control, here similar to the feeder 2 also. And then this is the open loop control set point limits. Here we have mentioned what are all the, here we have block 1, block 2, block 3, block 4, 4 incomers are there. So in incomer 1, what are all the inverter connected? So here we can set the limit, the operator set the limit, similar to the incomer 2, incomer 3 and incomer 4 also. Similar to the reactive power control also. In open loop we have only active power and the reactive power control only. And then this is the power control settings page. In power control settings page, as per the site structures, we have configured here what is the inverter peak active power and inverter peak reactive power, and similar to the in incomer 1, what are all the inverter connected to the, here we have mentioned inverter peak active power for incomer 1 and inverter 2, incomer 2 inverter peak active power and reactive power, here we have mentioned, and similar to the feeder 2 also. And then power control settings means what are all the set points in our logic. We have mentioned what is upper limit, lower limit of active power, gain reduction, critical limit, and similar to the reactive power control also, upper limit and lower limit, critical limit, gain reduction, tune step, and here we have mentioned. And similar to the voltage control set points also, and frequency control set point also, what are the set point limit, upper limit, lower limit, gain reduction factor, and the critical upper limit, lower limit, here we have mentioned. And this is the plant overview screen. In plant overview screen, we can check the operators, we can check each and individual inverter wise and MFM energy meter wise, we can get the data for the active power, reactive power, voltage, power factor, and current also we have checked this screen. And in system view, we can segregate two types of screen. One is field tag and another one is control tag. In field tag, what are all the in this screen, this dashboard is designed, we can get the all real-time data in field end, and we can visualize here, we can check, and the operators and the users to monitor and analyze the data more effectively this screen. Here in system view screen, we can also compare the block, each and individual block wise also we can check what is the active power and reactive power, and compare two blocks also, which block is more produce generate. Here we can also check and analyze the data more effectively. And this is the system view control text. In system view control text means what are the set point, the operator set the limit. Here we can check block wise also, we can check and compare these two blocks also. And energy meter, in control room we can check two energy meters are there, we can compare also two energy meter, what is the active power, reactive power, those things we have checked this control text also screen. And this is the trend screen. In trend screen, plant generation trends, block wise trends, and feeder wise trends. In plant generation trends, we can check overall the active power, overall the plant active power, reactive power, voltage, and frequency. Here we can check. In left axis we can compare overall active power, frequency, and voltage. In right axis we have checked overall the reactive power, plant reactive power, power factor, and radiation. Those things is the plant generation trends. This is the block wise trends. Each individual block wise also we can check the active power control and reactive power control. This trend screens, in left axis we have active power, and right axis also the radiation. Here we can check what is the block wise active power and their limit compared to the radiation. Here we can check block wise also we can check. And in another one trend screen is feeder wise trends. In feeder wise, in this 50 megawatt band, two feeders are there, each feeder has 25 megawatt. Here we can check energy meter 1 in feeder 1 and energy meter 2 feeder 2. Here we can check active power control, reactive power control. Here we can check in left axis active power and active power set point limit. In the right axis radiation and current also we can check. Here we can compare also these two feeder also we can compare. Similar to the reactive power control also, what is the reactive power actual feeder wise, and what is the operator set the reactive power limit to the feeder wise also we can check. And compared to the at the time of what is the power factor of feeder 1 and active power radiation also we can check. And similar to the voltage control, what is the voltage actual feeder voltage level and voltage control set point, and similar to the reactive power at the time of feeder reactive power, what is the radiation, active power, those things here we can check. Similar to the power factor control and frequency control also check the set point and the limit also check. Thank you.